All right, so I'm talking about this, scaling real-time data pipelines using Go. And really, what I'm going to be focusing the talk on is some of the problems we face while we monitor stuff at scale at Riot. So to give you an idea of like who I am, why I'm here, my name's Jennie. I'm a software engineer at Riot. I live in LA, which is where we're based. And I work on what's effectively our platform as a service team, trying to help folks inside Riot build stuff fast, build stuff that works, and build stuff without reinventing the wheel every time, which we have a tendency to do. And when you're kind of working in a system that's been around for a while, you have some issues both with scale and with creating like universal ecosystems. And we found Go was just amazing in solving some of these problems. So I'll talk through some of the things we ran into. If you are an expert at Go concurrency, then hopefully you can take lots of notes and tell me everything that I did wrong. If you know what a channel is but have never really played with them much, hopefully you'll learn a couple of things that we learned or things we did wrong that you can maybe avoid making the same mistakes. So yeah, if you want to get in touch with me and tell me all the things so I can learn and make our stuff better, that's my Twitter, Jennie Lees, and I'm Jennie Lees most places on the internet. And on the Summoner's Rift in North America, I'm known as Jelly Bear. So let's see if this works. Yay. So Summoner's Rift leads me to what is Riot and what do we do? Has anyone here heard of League of Legends? Oh, that's fantastic. That's really cool. Okay, so we make a game called League of Legends. For the rest of you, it's an online game, multiplayer online battle arena, which effectively, I think it was like an action strategy game with a lot of tactical work too. And we've been around for nearly 7 years. So we've grown from a startup to about 2,000 people. And it's a team-based game, so you play most of the time 5v5. We even have esports. So this is actually Wembley Arena last year for our World Finals, which I just think is freaking awesome that we could do this. And as you can tell by the fact that we can pack out Wembley Arena, we have a lot of people playing the game. So numbers, it's pretty big. These numbers are from 2014, so it's even bigger now. And as an engineer, I look at this and I think, shit, that's some scale. That's problems waiting to happen. That's legacy systems creaking at the seams. How do we make this stuff work? This is the worst screen in the game. When you're competitive, you'll work hard to achieve a rank, and you're grinding away at improving your rank, improving your gameplay. The last thing you need is to get disconnected from the game. And so I kind of think of my job sometimes as trying to stop this screen from happening at all. And if it does happen, monitoring it, alerting on it as soon as humanly possible, and figuring out the root cause so it doesn't happen again. Our players see it slightly differently. They're kind of fans of our server maintenances and server issues. And as someone working on the back end, and just Googling like League of Legends server problems, there was a million more things, some of which I couldn't even put in public presentation. The internet is very kind to us. So this makes me sad, and so I want to stop this stuff from happening. So monitoring at scale is the answer. That's one of the answers. And by monitoring, I mean monitoring metrics, logs, all that stuff. We heard a lot about yesterday, and we're going to hear more about today from other people too. But I wanted to put the word reliably in there, because as you start growing, you can run into limits with existing systems. And if your systems aren't working perfectly because of the scale they're at, you can't trust them. And if you can't trust them, then why on earth are you doing monitoring in the first place? If you've got false alarms going off or stuff that's delayed, your network operations center is overwhelmed with things that aren't even true, then you might as well just give up and have someone manually refresh or wait for the players to tell you. And we actually do look at things like the word people type in the word lag in chat a lot. It's one of the ways we detect lag. Obviously, we have network metrics too, but we found out that chat was a really reliable indicator as well. Although people do sometimes type it when they're losing. Can't think why. So we're a worldwide operation. We have a 24/7 global presence. We're played by a lot of people. And that means, from the engineering side, more numbers. The big circles are where we have multiple data centers. So grabbed these very rough numbers last night from our monitoring systems. So to some of you, these numbers might feel pretty small. To us, they feel pretty big. And from a company with a kind of startup history, growing into this kind of scale, it's been an interesting journey. We wanted to make sure that we not just account for the scale we have right now, but as we grow in the next few years, who knows what's going to happen and how these numbers might increase. I also wanted to mention that this is just our monitoring numbers. this actually isn't logs. This isn't business intelligence. This isn't player behavior data. There's a whole bunch of extra stuff, too, that goes on behind the scenes. And trying to make sure that both the things we work on interoperate the same way and speak the same kind of language, as well as scale in the same kind of fashions, it's been fun, especially because monitoring itself has kind of different use cases and different criteria and constraints than things like business intelligence. And I'll get into that a bit later. So, 160,000 services. A lot of them are microservices. And yesterday I heard the word microservices like 1 million times, so I won't kind of repeat it. But yeah, microservices are great. But once you have an ecosystem of microservices, how do you make sure that can scale gracefully? How do you create common things that people within that ecosystem can use to hook into the same pipelines without just dictating to everyone what they must and must not do? What does this look like architecturally? On a host, I hope this comes out okay on the side screens. On a host, we could have a bunch of different services. We have historic stuff. We have new stuff. We allow developers to do whatever the hell they want, pretty much. We let you use the right tool for the job, or your favorite language, or in the case of Golang, both, right? But we don't necessarily dictate any of that stuff, and we don't necessarily have a way to control it. So we end up with some fun constraints to work in. We have a lot of diverse tech stacks, diverse tech choices. We also have things running in different ways. We have containers, we have VMs, we have Metal, we have cloud third-party providers. We have probably things I don't even know about, to be honest. And because we're a games company, we have Windows, and we have some Mac stuff too. And coming in out from the outside world, from tech, moved from San Francisco to LA, fresh off the startup boat, I was like, hang on a sec, you're using Windows? My desktop is a Windows machine? It certainly gives us some fun constraints to work in. And we have a mix of stuff that we built in-house and stuff that we bought open source, things we've forked, things we're literally paying money for. And some of that stuff we have easier ways to control and change than others. So problem, how do we consolidate things like monitoring and microservice support systems with all these criteria? We solved it pretty much the hardest possible way, which is by getting humans to agree on something, especially getting engineers to agree on something. And what we agreed on was this: 2 agents on every box, service discovery, and metrics. Pretty simple. And that's kind of like a given. There's always going to be there. We also agreed on contracts. So aligning around standards of how these services interoperate. We decided on HTTP and JSON. Because of the sheer diversity of things we're working with, that was the most universal choice, especially at the time. And we agreed on a bunch of ways that you have to expose your metrics, you expose your health, you expose your ID information, even your configuration, so we can pick that stuff up and do things with it. For services like Memcached, which we don't necessarily write ourselves, we wrote sidecar apps that know how to translate that app stuff into our universal standard. And we deploy those alongside the original apps so that we can pick up their data in the same way. So what does that actually look like? So we have service discovery. The metrics agent goes to service discovery and figures out who's running. Service registers at service discovery, tells it where its metrics endpoint is, and then the agent goes straight to the service and exposes effectively schemaless JSON. Is nested in a certain way, but that's about it. You can put new stuff in, you don't have to declare it. We'll just pick it up and add that new thing. So we have a lot of developers using things like feature flags and dynamic configuration to add in new metrics on the fly, which has been pretty cool to see. What happens next? So agent pushes stuff to collector. Collectors are at the data center level. The collectors then push to a global store, which aggregates everything, and we build alerting and dashboards on top of that. Some of the internals, we use HTTP JSON between the agent and the collector, and then we have a Kafka queue from the collector to the global store. Our old system kind of stopped at the data center level because the number of values per second it was trying to process at a single data center was already overloading it, and we couldn't possibly take it global and say, how do we aggregate this thing? We ran into issues with MySQL, even using things like Fusion IO cards. Our databases couldn't get big enough to store the data we needed. And we just sort of thought it's about time, let's get with the program, let's use things like Kafka, let's use Elasticsearch, we use Kibana, we use Grafana, had some some good love for Grafana yesterday. It's one of my favorite tools. And we use some custom stuff on top of that too. So the right-hand side is kind of open source stuff that we've bought and we use heavily. But the first two pieces we wrote ourselves, partly because of the constraints we're working with, partly because of the contracts we're trying to obey, and partly because we're engineers and we like writing things from scratch when there are off-the-shelf solutions available. Why not? So when we started writing this stuff, we had a few different goals. We wanted stuff to be decoupled. And that kind of seems like a no-brainer, but our old system actually wasn't. And we ended up having to make box-level deploys to change small things with our data store format. And that just felt so wrong. We're very, very glad. Like, first goal was, let's not do that. We also wanted to be decoupled internally so we can make changes easily. We wanted to be resilient. So we kind of trust some of our internal networks, but we don't trust all of them, and we certainly don't trust links from the data centers to the outside world. I mean, DDoS attacks are a thing. Switches dying are a thing. Like, the real world is messy and horrible, and you have to make sure you can deal with that. So our original plan was like, let's just push straight to Kafka in the cloud. Oh wait, what happens if stuff goes down? Do our game servers have to start buffering stuff in memory, and then game server runs out of memory, and then people get kicked out of the game, and engineers cry, and all that stuff. So we don't want that to happen. We want things to be HTTP native. HTTP and JSON is our language, so we wanted to pick a language or a framework and language that would work with that out of the box. Again, sounds a little bit obvious. I'm kind of preaching to the converted here, but when I first came in, we were using C++ for this. It was not fun. So don't use C++ for HTTP stuff unless you're doing a bunch of other stuff too, which we were. Also instrumented. We want to eat our own dog food. We need to know what's going on inside of our pipeline, both at the service level and inside the services themselves. And part of that is around making sure that the architecture and design of the services is something that people like our network operations center can look at and say, hey, this thing's backing up. This thing's not working super well. Let's get someone on the pager, let's fix it. Without just being like, my metrics aren't working, what's going on? Which was a frequent complaint before. And obviously fast, because we have a lot of traffic, we're gonna have more traffic, we want things to just be fast, be fresh. So this is where the kind of use case of metrics versus logs versus BI and stuff comes in, because metrics, especially if you're alerting on your metrics, you need them to be up to date. If something goes down, you want to know about it like instantly. You don't necessarily want to have like 1 million more messages in the queue that you're processing. So we need to be able to be fast and scale. So Golang. We looked at those criteria and we thought, well, we're already using Go. Go is kind of just a no-brainer. I don't need to tell you guys that. So Go save the day. And I'm going to talk a bit about some of the tips and tricks we found out when using Go to do this. The TLDR, if you want to leave now, is just channels. Channels are great. We use channels a lot, and maybe a little too much, so we'll see in a moment. Visualizing channels is hard. This slide has gone through different iterations to say how can you kind of represent a channel well. So I came up with this conveyor belt factory thing. It needs a bit of work, but bear with me. So inside our service, we have a poller that goes out and checks the host for the metrics. Transformer thing that turns those into specific events according to a schema, and then a pusher that sends those out. We decouple them, we use buffer channels to keep stuff flowing. Inside the collector, it's pretty much identical. We receive stuff, we do some transforming, and we put it onto Kafka. And there's a bunch of other channels and concurrency in here. It's not just these two kind of conveyor belt things. The other thing that is interesting about this is these two services are totally separate. So if I'm a service and I want to send my metrics directly to the collector, I can. I'm not going to stop you. You don't have to wait for someone to come along every minute and say, what's your metrics, what's your metrics? You can miss a bunch of stuff that way. And you can also send things like logs, because this is just generic events now. You can send logs, you can send changes, you can send anything really. And so we're moving towards this fantastic place where we have logs, metrics, some BI stuff, behavior stuff, all in the same place. So we can literally look at things like someone saying lag in chat next to a network spike, next to a detected DDoS attack, next to some metrics saying our response rates are timing out, and get a really good picture of what's going on, which gets us back to that problem of how do we stop this stuff from happening again? How do we know what's actually going on to avoid us, especially in the microservice world, trying to squash the wrong thing? Like, oh, this thing's slow, it must be this thing's problem. Well, actually, no, it's a downstream dependency. That's the problem. So let's get to some code. Code is fun. So here's some of the patterns that we ran into. Rate limiting. So on a game server, you don't necessarily want to slam every single part of the game server with a concurrent request to get metrics at once. You want to kind of balance the load, especially if you're only polling once a minute. It just doesn't make sense. And we have these huge buffer channels, 100,000 plus items long inside our service. We don't make 100,000 requests. That's kind of crazy. And so we found this cool pattern. And like, none of this stuff is rocket science, by the way. We all got this from like the internet. We didn't make this up. So credit, if you were at the blog post that we got this kind of thing from, I love you. But I wanted to share this stuff because it's awesome. So you create a smaller channel, and you have a Go routine that just kind of reads stuff off the small channel, puts it on the big channel. And then you take advantage of natural blocking. That's kind of neat. It's just going to block on that bottom piece until the previous one finishes if the channel's full. It's kind of magic. It's very elegant. And obviously not the only way to do it, but I just found this was really cool. And you don't need to change internal channel sizes, so you can keep that decoupling there. Caching. This is a fun one. So we have service discovery. We need to keep a list of those services. We don't want to poll service discovery every single time we're polling services, although we could. We don't want to. So we keep a little cache, effectively. And we, first of all, came across this pattern where you say, request response, give me your stuff, here's your stuff, and then at the same time, a separate channel to say, here's some new stuff, update the cache. And this runs in a single Go routine, and therefore you don't have any contention or weirdness, and everybody's happy. Except for when you scale, and the read starts blocking because your consumer is slow or doing stuff, and you have to basically trust that the thing reading off the output channel here is going to behave, which is not necessarily something you can guarantee, and certainly if you want to handle thousands and thousands of requests a second, it's just not particularly efficient. And so we found this was a bottleneck, and we were like, oh, that's strange, we're using channels, channels are great, what's wrong with this? And my team member says, oh yeah, data's fresh, good. A team member says, why don't you use mutexes? And I'm sitting there drinking my Golang Kool-Aid and saying, I am never using mutexes again. Channels are the word of God. I'm never going to touch that stuff. Get back to Java land or whatever. And we had a pretty educational discussion from this, because it turns out mutexes are actually pretty awesome. They're pretty Golang, like native, and they work really well for this situation. So don't be like me and too proud to consider them. We ended up with this rewrite mutex, so you can have an unlimited number of readers or a single writer. And so you can parallelize your reads while still making sure that you have a single Go routine managing things like the updates and writes. And I'll probably put these slides online later, or you can ping me on Slack if you want to get some of this stuff. So, talking of refreshing, so we're going to go refresh our service data, or we're going to poll. We have a kind of ticker pattern. So we want to make sure that we run this thing every 5 minutes, say. So we use time not after, when it pulls off a channel and then runs the thing. But when we first ran this code, we realized, this is funny, our service isn't working until 5 minutes have gone past, what's going on? And we ended up having to call it again beforehand, because time not after is exactly what it says, it only runs after that time. And I see this in a code review and I'm like, what the hell, this just looks wrong. But it turns out like this is the best way we found to do it. And some of you might be thinking, I hope, why are you using time.after instead of time.tick? And this is one of those things where looking through this to do the slides, I'm like, wow, we should have been using time.tick. I tried some profiling yesterday, and I'm looking forward to the talk on profiling later, because I think I might learn some things there, because I found that there's practically no difference. So, good to know at least. Orchestration, so linking this stuff together. This is a pretty standard thing. There's like a bunch of blog posts and things about Go pipelines, and they all kind of look a bit like this in the end. And it's just so simple and elegant, I love it. And what we're doing here is saying, we're running a data pipeline. We don't want to just kill everything. We want to make sure that stuff gets from point A to point B to point C, and then we shut down gracefully. So we use an exit channel, and our Go routines listen on that channel and do stuff. We use a chan struct, and this is something I learned, that we started off doing a Boolean and listening for a true signal, but actually you can just close it, and that will also trigger the select. So if you didn't know that, good tip. If you did know that, then you're a step ahead of me when I first started working on this. The problem is, if you look at this, maybe our push work is going to stop first because it's more efficient, and our stuff earlier in the pipeline might never get sent through. Maybe something further down the pipeline is actually going to close a channel that something else is writing to, and we don't want that to happen because that's a panic. So we tried to find a better pattern for this. And, oh yeah, this is how it looks inside the service. So you say, case return. When it's closed, it triggers that. And it's super, super readable, which I really like. So we found sync.waitGroup. And sync.waitGroup is like my new favorite thing in the sync package, because it's effectively just a big counter. You say, I'm going to add a thing every time I start something, I'm going to take one away when I finish something. You have to make sure you're careful with your defers or whatever to make sure it actually calls the done function. We ran into that a couple times where we didn't do that and things broke and we didn't know why. So think about when you're actually like saying you're done with that. But yeah, then you can just wait until it's done. The other cool thing about this is we can do this two ways. We can have multiple channels for every part of the pipeline, which is very readable and very clear. Or we can close the internal buffers and use range selects. Like we can effectively say, nothing more is going to write to this because I completely and utterly trust that I've waited for it to stop. And then I can just close it, and that simplifies the code. And it depends a bit on how your code's structured, which one's going to be best for your use case. We ended up doing a mix of both, but refactoring into some of the closes made things a lot cleaner. That's what I just said, yeah. We also found channels fun when we were sending stuff out over HTTP. So we don't want to send a single item every single HTTP request. That's kind of crazy inefficient, and why would we need to do that? So we want to batch things. And we're like, oh, buffers. We've got buffers, we've got slices. We can just fill up a buffer and then send it on, and fill it up and send it on, kind of like filling up a train in the tube or something. And we use the ticker. Here, apparently, we did learn what tick was. So we use a ticker to make sure that we don't like wait around forever for one new item when we have fresh data that could be sent. So this worked okay, although the code kind of looks a bit weird sometimes, but it kind of worked pretty nicely. And we found it was a little bit of a bottleneck, and the data wasn't coming through as fast as we wanted it to, and we kept like reducing the size of the ticker timeout. Eventually, we ended up sending like 2 items at a time, and wondering, what are we even doing here? This is not going to scale. And we realized, hang on a sec. Let's think about what we're sending here. We're sending a bunch of metrics we got from a JSON endpoint. That is a natural batch by itself. So why don't we just use that as the batch? Then everything's together, it arrives at the same time. We can figure out what's going on if a specific batch is delayed. And we can use buffer of slices instead of individual items, and that actually makes our upstream code a little neater too. So we were trying to get too clever. We were trying to go all channels and buffering and filling things up, and we're like, actually, we don't need to. And that goes back to thinking about like, what kind of things you're trying to do, and what are your priorities when you're handling this kind of data. And when you think about things at scale, like, you're trying to optimize around batching, you're trying to optimize about throughput, you're trying to optimize around making sure that when stuff does go wrong, you do the right thing. And you know when to quit. You know when to throw things away and drop them on the floor. And for some use cases, dropping things on the floor is absolutely terrible. You never want to do it. For metrics, we're actually kind of okay doing it. We don't like it. But if the data center's link is down, we want to make sure that when it comes back up, we don't have 4-hour-old data coming through. We want instant alerts. Especially because the 4-hour-old data will fire off alerts that aren't true anymore, and then the NOC gets really angry, and our lives are not very fun. So visually, the conveyor belt again, we've got full channels, stuff is blocked. We just throw away some stuff, and then new stuff can go in. And we struggled for a few ways to do this, kind of using managers around the channels, sort of running separately and inspecting them. And again, we kind of thought a bit more about the logic here and said, well, if a send is failing, then stuff's going to start backing up. So when a send fails, we can check and see what's going on in the buffer, and if it's getting pretty full, we had like a dynamic saturation number that we played around with, and we just start throwing things away, just receive into nothing effectively. And you can tune this dynamically. You can say, hey, maybe we know something's wrong, so let's update the like draining threshold to be super low, or even to 0, so that as soon as stuff comes back up, it's fresh and we lose the interim, but we know that stuff is broken anyway. So we can play around with that, which is nice. Dynamic configuration helps a lot with this kind of stuff. So did we manage our goals, and how did Go specifically help? Well, decoupled, yes. And using a lot of things like buffers and interfaces, we managed to keep our internal structure super decoupled, super easy to work on different parts at the same time, which has been really fun. And between our services, we have very clear contracts and clear separation of concerns. We don't know what the data store does. We just put things in Kafka. And we actually changed our data store a couple of months into this process. And it was a one-line dynamic config change. That was it. Which, compared to previous systems we were working with, was like a dream come true. It was amazing. We wanted to be resilient, so we do things like batching, draining, and this is a totally stateless service. So we can run it horizontally. The local agent, not so much, but the collector you can, and that's the piece that gets the most contention. So you can run like 500 of them if you want, and you can dynamically spin things up as data starts getting, like during peak time we run more games, so there's more data, so we can spin up more collectors and then spin them down again later if we want. HTTP native, it's Go. It's been super easy to work with HTTP. I don't need to preach to converted on that one. And we use internal metrics around our channels to help both dog food our service and to help expose what's going on. And because it's kind of easy to reason about what's going on, it's been very easy for folks who don't know the internals of this service to give us good reports on what's going wrong in our data centers and say, hey, look, this thing's starting to fill up. My Grafana graph's going up. Can you look at it? Finally, fast. So I load tested this on my laptop last night, and a single instance running on Docker got 75,000 values a second. If you remember the slide with all the numbers earlier, 100,000 globally. So basically, I can just put my laptop in the data center and we'll probably be okay. If I close down Chrome, I think it'll be fine. That's not actually how our data centers work for anyone that's one of the players that's been affected with some of our recent fun. But it's been very, very encouraging. And Go, especially, has helped us with this. It's very easy to tune and profile some of it. So scale provides some challenges, but really it just helps you think about the way you design your service. And once you actually start using these kind of concepts, the scale isn't really that important. Like you could run this thing in 10 values a second and it would still work pretty well. You maybe wouldn't have made all the same decisions, but the scale itself is more just a function of the design than something that causes too many problems when you're working with Go. So we've had a lot of fun with this. And we're hoping this is going to scale out to millions and millions of values at some point, and I think it certainly horizontally will. So thank you guys for listening. If you have some stuff to help me improve this, I would love to hear from you. And if you have any questions, I'm happy to chat afterwards. Thank you guys so much.